to calculate the Fourier transform of Dirac-delta function, this D should be capital because this is the name of the person, Dirac. And this delta function was defined by this Dirac. So let us first see what is this. What is Dirac-delta function? And how can we define this? So this function is also known as, firstly, this is also known as an impulse function. What is an impulse function? Impulse function is that which represents an instantaneous force at a certain point. For example, we have in many applications the force which is exerted at a certain point, and that force is infinite in nature. So that means suppose there is an earthquake occurring. So what we do, we represent this force through an impulse. Say suppose this is the time axis, this point is 0. We say at the time 0 we have a sudden impulse. So your impulse would something be like this. This also goes to infinity, right? So your impulse would something be like this. So at this particular point we have an infinite amount of force acted upon it, and at all other points it is equal to 0, right? So this is the impulse function or the Dirac-delta function. Suppose the earthquake is felt at different time periods, so it is like this and then this and then this. So at all these different locations, say A1, A2, A3, an impulse is felt of different amount. So this represents, denoted by delta of t. This is equivalent to 0 at all the points except 0, and it is equal to 1 whenever t is equal to 0. So when the magnitude is restricted to 1, this is known as the unit Dirac-delta function, right? And otherwise its magnitude here is infinite. So this is the definition. So moreover, the property is that if we take its integration from minus infinity to infinity of this function delta t dt, this is equivalent to 1. So that is what we are saying. That is, we say it is a force of 0 duration. That means it occurs instantaneously. It is a force of 0 duration which is only non-zero at the exact moment at t is equal to 0 and has strength of 1 unit. In fact, total strength of 1 unit, or total impulse of 1 unit. So this is the Dirac-delta function. So now similar to this, we have translation. We have translation of this Dirac-delta function, delta of t. So what is this translation? The impulse can be located at an arbitrary time rather than just at t is equal to 0. So we are saying at some other point also the impulse could be there. Suppose for an arbitrary impulse at t is equal to c, the Dirac-delta function at this position, which is displaced from 0 by c units to the right, that is defined as 0 whenever t is not equal to c, and it is equal to 1 whenever t is equal to c. So that means we are saying if this is your y-axis, this is your t-axis, then your function now is situated at, the impulse now is situated at this length c, right? And it is 0 everywhere else. So this is the meaning for this translation of the Dirac-delta function. Moreover, we have this condition that if you take the total area of this impulse from minus infinity to infinity, it is going to be equal to 1. Why? Because at all other points we have 0, but at only one point its value is equal to 1. So when you add up 0, 0, 0, 0, 0, 0 and 1 to it, you will have the value as 1. So this is about Dirac-delta function. Now let us have a look at the relationship between this Dirac-delta function and the unit step function So for that, what we do, we define the Dirac-delta function like this: delta kt, where what is this k? This is 0 whenever t is less than 0. Whenever t lies between 0 and k, its value is equal to 1 by k, and it is equal to 0 whenever t is greater than equal to k. So this is the definition for Dirac-delta function. So now you see, how can we define this function graphically or in terms of unit step function? So in terms of unit step function, this delta kt, this is defined by 1 by k as such. And what is this thing? This is nothing but 1 by k, and it is defined like this: 0, 1 and 0. And whenever t is less than 0, t greater than equal to k, and t lying between 0 and k. And what is this? This is nothing but the unit step function defined in this interval. So how can we define that particular thing? So it is 1 by k, the unit step function at the point t, minus the unit step function at the point t minus k. Let us see it how. So this becomes unit step function at the point t minus the unit step function at the point t minus k, which is something like this. So it would be, this is t, and what would be the graph? Say this is the point k and this is the point 1 by k. So your function between the interval 0 to k, its value is equal to 1 by k, and otherwise it is equal to 0. It is 0 here, it is 0 here, and it is 0 here, right? So the function is defined like this. Now how this is equivalent to this quantity? Let us see how. So if you draw this thing, u of t, what would be u of t? U of t multiplied by 1 by k, it would be equivalent to 0 whenever t is less than 0, and it would be equivalent to 1 whenever t is greater than equal to 0. But here it is multiplied by 1 by k, so we have the magnitude as 1 by k. And what is this? 1 by k u of t minus k. This is equivalent to 0 whenever t is less than k, because we have shifted it by k units, and it would be equivalent to 1 whenever t is greater than equal to k. But the magnitude here has been multiplied by 1 by k, so it would be 1 by k. So this is the definition. What would be their subtraction? Their subtraction would be, let us see their graph. The graph of first one, that would be like this. This is 1 by k u of t, and this is t. So whenever your t is greater than 0 or less than 0, the value of the function is 0. And whenever it is greater than 0, say this is the point 1 by k, so its value is equal to 1 by k. This function would be like this. This is the t-axis, this is 1 by k u of t minus k. So whenever your t is less than k, the function's value, it is equal to 0. So the function's value is 0, and whenever t is greater than equal to, say this is 1 by k, so the function's value is this one, right? So when you subtract these two, let us see what do we obtain. We obtain another graph having t-axis as this one, and this is the subtraction of these two, u of t minus u of t minus k, right? So this point is 0. So whenever your t is less than 0, here the function's value is 0, here the function's value is 0. So 0 minus 0 is 0. So our function here in this interval is 0 only, right? Now let us see it for this interval 0 to k. In 0 to k here, say suppose this is k, the function's value is 1, and here the function's value is 0. So that means the 0 minus 1. So the function's value would be, what would be this one? It would be 1 here, right? Because it is 1 here and 0 here, so this minus this is 1. And from this interval k to infinity, the function's value here is 1, and here also it is 1. So 1 minus 1 is 0, or 1 by k minus 1 by k, that is 0. So the function here is defined like this. So this function is exactly same as this function. So that is why we have written this relationship between the Dirac-delta function and the unit step function. Now how this is equivalent to Dirac-delta function? This is defined using k. So what if I take k tending to 0? So I have this definition now. I have this definition, delta k t, that is 1 by k u of t minus u of t minus k. And what is this delta kt? This was defined to be like this: 0, 1 by k and 0. Whenever t is less than 0, t lies between 0 and k, and t is greater than equal to k. So these two results are there. Now what if I make k going to 0? So whenever this k goes to 0, the length 1 by k, this will tend to infinity. So that means your duration of this interval that goes to 0 and the height of this interval will tend to infinity. So whenever you make this condition, the this interval is reduces to 0, and the height of this interval, this goes to infinity. So that means we say whenever k tends to 0, we have the limiting value, limit k tends to 0, delta kt. This is nothing but the Dirac-delta function itself. So this becomes equivalent to Dirac-delta function. So, and this is equivalent to the impulse at the point, t is equal to 0. So this is the definition for Dirac-delta function in terms of unit step function. So in terms of unit step function, this becomes u of t minus u of t minus k divided by k. So this is the definition for this Dirac-delta function, because the value of del kt was this one, right? So this is what we obtain from here. So one thing that should be noted here is, note, here you can see this is this resembles the derivative. This resembles the derivative of unit step function, and it is not the ordinary derivative, but the generalized derivative. Why this is so? Because the ordinary derivative here, that does not exist due to the presence of discontinuity. The ordinary derivative does not exist at t is equal to 0 due to discontinuity. Hence we can also say that u dash t, this is equivalent to delta of t, and u dash t minus a, this is equivalent to delta of t minus a. And moreover, we also have this one property, this is known as filtering property. So this property says that if f of t be any continuous and integrable function in the interval 0 to infinity, then integration from 0 to infinity of f of t of that function with this shifted version of Dirac-delta function dt, that is nothing but the function at that point. So if you multiply any function with this Dirac-delta function, what does it mean? It means that your function is only defined in that particular impulse. So suppose this was your function and the Dirac-delta function is defined at a single pulse at this point. So whenever you multiply this by this function, so you would have the function's value only at this particular point. So this is the Dirac-delta function multiplied by f of a. So this is the meaning for this thing. Now we are interested to calculate what is the Fourier transform. What is the Fourier transform of Dirac-delta function? So for that, what we do, we take its Fourier transform. So that would be the limit k tending to 0 of 1 by k, the Fourier transform of u of t minus u of t minus a. So this is by definition, and because we know this Fourier transform is a linear transform, so that is why we have took this term 1 by k out from this Fourier transform operator. So this becomes limit k goes to 0, 1 by k, and what is this function? This is only defined from 0 to a. Its value is 1 from 0 to k. So 1 into e to the power minus iota omega t dt. This is by definition for Fourier transform, right? So we have this term, then we can simplify this. So limit k goes to 0. This is equivalent to 1 by k e to the power minus iota omega t divided by divided by minus iota omega, and the limits varies from 0 to k. What is this function? U of t minus u of t minus k, we have just seen this is equivalent to 0 whenever t is less than 0. It is equivalent to 1 whenever t lies between 0 and k, and it is equal to 0 whenever t is greater than equal to k. So this is this function, right? So we have used this definition over here and applied the Fourier transform to calculate this thing. Then we have performed the integration and substituted the limits. After substituting the limits, we have limit k goes to 0 minus 1 by iota omega as such, and then e to the power minus iota omega minus 1. So now when you substitute the limits, that is whenever k goes to infinity, the term becomes 0 by 0. So here we will apply the L'Hopital's rule, which says that you have to differentiate, in order to calculate this limit, you have to differentiate the numerator separately and the denominator separately. So we would have minus e to the power minus iota omega k into iota omega. That is the derivative of this particular term, and the derivative of this term would be 0, and in the numerator we will differentiate it separately, so its derivative would be the derivative of not this term but 1 by k, right? Because k was creating trouble whenever your limit was equal to 0. So the derivative of k is 1 and 1 into omega as such. So from here we obtain this, and this cancels, minus and minus cancels. So we have limit k goes to 0 e to the power minus iota omega k, which is equivalent to e to the power minus 0, which is 1. So from here we obtain the Fourier transform of delta of t, that is equal to 1. So this is one formula that one should remember. Moreover, from here we can also say that the Fourier inverse of the number 1, that is equal to the Dirac-delta function. This is also one of the important result.